Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to really dive into the ideas of how we can use our molecular weights and chemical formulas to determine a lot more about the composition of a species or even of a mixture. So one of the good places to start with this is one of the most frequently used descriptions of either a molecular species or a mixture. This is percent composition. This can literally be thought of as the amount of a given component in a total system. So one of the more common things is if you're looking at a solution, the amount of a dissolved species in a whole mixture. So the amount weight of, for example, hydrogen peroxide. So if you have a system that's 3% hydrogen peroxide by weight, it means that you've got 3 grams of hydrogen peroxide per 100 grams of solution. However, you can often use this to describe not just solutions or mixtures, but also individual compounds. So, for example, I might want to know how much of that hydrogen peroxide is hydrogen and how much of it is oxygen. So one of the ways we can do this is by using our percent mass, but in a slightly different form. And this may look fairly familiar, as this is the description of chemical compounds that was originally used way back in chapter 2 when we were deriving the composition of species and ratios. So in this case, we can find the percentage of a given element in a species by taking the mass of that element in 1 mole of compound over the mass of 1 mole of that compound. So the mass of 1 mole of the compound is going to be fairly easy to figure out. That's just the molecular weight. However, the mass of a given element is a little trickier because we need to know 2 things. First, the atomic weight of that element, and also how many moles of that element are in a given mixture. So for example, let's say I've got something like nitrate. So nitrate is a nice negatively charged ion, it contains 1 nitrogen atom and 3 oxygen atoms, which means if you're trying to determine the percent weight of nitrogen, we only have 1 nitrogen. But if you're trying to do it for oxygen, we've got 3 oxygens. And one of the things that's useful is that this can help generate experimental masses. So if I want to try and figure out what system I'm examining, I often need to figure out these percent weights. And I can compare either a measured percent weight versus an ideal one to get an idea of purity. If the values agree very well, means I've got a pure compound. If they disagree, it usually means that somebody is off. Either I've got too much of a contaminant or I have too much of a given species. And there's also a lot of reasons why these percent weights can be important. For example, if you're looking at levels of nitrate pollution, which is an important feature of agricultural runoff, it's almost always given as a percent weight of nitrogen in the water, not nitrate, but just the nitrogen. So that means if I'm trying to relate the amount of nitrogen to nitrate, it's very important to know the percent weight of nitrogen and oxygen in nitrate. So we can do this by starting off by knowing that nitrate has a molecular weight of 62 grams per mole. So I can find the percent weight of nitrogen simply by taking the atomic weight of nitrogen divided by the molecular weight of nitrate. So this means that my nitrate is about 23% nitrogen. Similarly, I can do the same process with oxygen, but now I note that I've got 3 moles of oxygen per 1 mole of nitrate. And so I then use the molecular weight of oxygen to give a percent weight of 67% oxygen. Add these 2 together and you should get 100%, and turns out we do. But this is a very important feature. So this means that if you're going to report percent weight of nitrogen in nitrate and water, this should be about 1/4 of the percent weight of nitrate. This makes it very important whenever you're dealing with percent weights that you're very clear of whether you're dealing with an individual element or the whole molecule. Otherwise, you can get in a little bit of trouble sometimes. So one of the other things that's worth noting is when you're dealing with percent compositions, it's also very important to note when you're dealing with percent weight, because there's another less common percent composition, and that is molar percent. So for example, if I'm working with a lot of radioactive species, it's very common to say something like potassium has an isotope called potassium-40. It's actually fairly radioactive, and it's the dominant source of most radioactivity in the body, because it turns out that about 0.012% bimolar ratio of all potassium is potassium-40. So this is very important if I want to know what my average everyday exposure is. So for example, let's say I like to eat a banana every morning, which I do. That banana tends to contain about 422 milligrams potassium. I want to know how many of those potassium ions are going to be radioactive. So I can start with my potassium, mass of potassium, and then I can turn this into moles, knowing that certain mass of potassium gives a certain number of moles. And then I know a certain molar percent of that potassium is potassium-40. So for example, I know it's 0.012%. So that means 0.012 mole for every 100 moles of potassium, I've got 0.012 moles of potassium-40. And then I can turn that number of potassium ions into that number of moles of potassium-40 ions into actual ions. So it turns out that in an average banana, you're going to be eating about 7.8 potassium ions. So really not as many as you might think, but it's still fairly important to know. So one of the last important things when we're looking at mass, the relationship in between molecular formulas and percent compositions is that you can use your molecular formulas not just to determine percent weights, but also mass ratios, which again is often, which we used originally in the law of definite ratios to figure out the identity of molecular species. So let's say I want to try and figure out the mass ratio in between carbon and oxygen in CO2. So for every 1 gram of carbon, how many grams of oxygen might I have? We're going to do the same process of unit analysis. I can turn grams of carbon into moles of carbon. Then using my molecular formula, I know that for every 1 mole of carbon, I've got 2 moles of oxygen. And then turn moles of oxygen into mass of oxygen. So for every 1 gram of carbon, I've got about 2.7 grams of oxygen. However, it's also possible to do the reverse. I start with a mass ratio, and then I can use this to determine a molar ratio. So let's say that I know that glucose has a mass ratio of 0.75 grams of carbon for every gram of oxygen. Well, I can put that in as a ratio and then use my molecular weights to turn grams of oxygen into moles of oxygen and grams of carbon into moles of carbon. Doing unit analysis, we'll note that grams of oxygen carbon both cancel out, and I'll be left with moles of carbon over moles of oxygen. And it turns out that carbon and oxygen are in a 1-to-1 ratio. As we've seen before with the molecular formula of glucose, it has 6 carbons and 6 oxygens. So this actually turns out to be just right. And it gives us a very good starting point in trying to, if you measure a percent mass, turning it into a molar percent or a molecular formula. So next time, we're going to be talking about how you can use measured values of percent masses and develop chemical formula. Until then, take care.